the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 66, where today we're going to be talking about gravity waves.
Wow.
This was something quite kind of interesting because I believe Parker can tell the story of how we thought of this episode, because we didn't.
Well, actually,
Right?
we were on Instagram Live
Exactly.
on Monday, right after the last episode got posted. And then somebody in the comments said, do gravitational waves. And I was like, okay, sounds like a fun podcast. And so now we're here talking about gravitational waves.
Yeah, I mean, gravitational waves, especially recently, because, not even pre-Einstein, but even after Einstein released like his general relativity, that was a big question mark, right? Like, even though gravity was understood, but him saying that, hey, listen, it's not really, it's not really an attractive force. It's just some consequence of mass traveling on this manifold that we call space-time. Like, that idea was kind of new, right? And like this whole transition into today where we now, accept gravitational waves as something because of Ligo and things like that we're going to get into, and black holes that we now have seen and witnessed.
Yeah. And the history of physics and how physics unfolded is one of the most interesting things ever. Because you learn a lot of things in school. Obviously, we didn't know these things and since the dawn of time, and a lot of these things have come up very recently, which is why quantum mechanics is so exciting. Right? Because these things have, in the big picture of the science timeline, quantum mechanics just came out. So we have no idea
80s or something.
What is, well, no, not the 80s.
Okay, a little earlier, it really picked up in the 60s, 70s, right? It really picked up in this...
it actually started back in late 1800s with Max Planck.
Yeah, but I'm saying it picked up. When did quantum mechanics? People were really talking about quantum mechanics, kind of like Niels Bohr time, right? 60s.
Yeah, Einstein, Bohr.
Yeah.
That was the 20s. Yeah.
Oh, that was the 20s. What am I? Then 60s,
Yeah,
maybe. Okay, then I think I'm a little too late. I think I'm going a little too late. Sorry, continue.
Yeah. Anyways, the history of how things came about and how physics is evolving right now. What's going to be next? Nobody knows, right? Somebody comes out with time 2.0, right?
Time 2.0.
Who knows what's actually going to...
No, but cool thing about...
explain literally everything.
Cool thing about gravity waves, though, is that this thing was predicted, back in 1915. And then it was, it was proved. Well, even I guess quantum mechanics, a lot of experiments have been observed to be true. So I guess you can say that for that. But when talking about gravity waves, the first real prediction was with the whole black hole merger in 2015, right? So 100 years after the whole thing, which was kind of a cool number, it was a clean 100. So it was kind of interesting.
Was that the very first?
Well, technically, general relativity was 1916, but it was kind of, anyways, the ball's out on that. Yeah.
I'm saying was that the very first prediction that was confirmed?
Yeah, in 2015 is when we saw, or not saw, the black hole picture was later. I'm saying 2015 is when 2015, right? Am I missing up the date? I'm pretty sure it's 2015 when the first gravitational waves were detected off the merger,
if there's
right?
any other prediction that was confirmed earlier than 2015.
I don't believe so. Because I think a crazy thing with Ligo... If I'm not I think a crazy thing with Ligo is that they had actually shut it down for quite some time, and then when they had come back up, they had started it back up, 2 weeks later, they got the black hole merger. 2 weeks later, 2 or 3 weeks, it was really soon, basically, right after they revamped the facility, because they just wanted to I believe they remodeled the whole thing. So I think this that was a pretty cool story. Because it was so recent, but that was still a monumental discovery. And no, I do not believe it was done before that.
All right. Well, before actually talking about gravitational waves, let's get into the news segment of the week.
Yep.
first of all, we're almost at 150,000 downloads. So thank you so much, everybody that has been downloading the podcast. We are also at 9,900 followers on Spotify.
Decent.
So close to 10,000.
Oh my. By the time this episode
10,000
comes out, no, probably not.
Maybe.
You think so?
Maybe. Actually, maybe. There's a good chance. But what I was trying to say is that when we do hit 10K, here's a little sneak peek.
Oh, you're telling him?
We might be dropping a little bit of merch. Oh. Yeah, that's right. A little bit of merch might drop at 10K. Keep your eyes peeled on Instagram at math.physics.podcast for all of the details. Little giveaway. Make sure to check it out there. Also, other than followers and downloads, or speaking of, make sure to hit that follow button, hit that subscribe button, hit the like button.
For sure.
Hit the comment button, start typing, and then hit enter. I don't know.
Yep.
And
let's do it.
Also,
hit that bell icon too, right? Or whatever. Because even that, I think that
we're so good. We're so good at this.
So good. We're just figuring it out. So the comment of the week this week is quite interesting. Let me just say that. It's by none other than Aryan Raj, who says, "Wow." I just love the comment. I just love that.
I think we're running out of comments here.
No, but it's a very nice comment. So thank you, Aryan.
For sure.
For that comment. And as usual,
if you want to be comment of the week,
all you need to do to be part of the comment of the week is just comment on the most recent episode, or to be honest, like even a clip. Like if we really like it, like we can still pick it, but usually we look on the episodes. So comment on there, let us know, and you might be picked for the next comment of the week.
Definitely.
Who knows?
Anyways,
let's get into it.
Space-time curvature. You hear about it all the time.
Okay.
You hear these fancy physics guys saying space-time is curved by mass, but what's happening, okay? Well, space as we know it is three-dimensional, and time, we consider it as a fourth dimension, and then we exist on this four-dimensional manifold. And it's not actually the space that's curving, right? It's the space and the time together, right? Mm-hmm. That's curving. So, for example, one way that you can peer into more complicated topics in physics is to analyze light, because light for a very long time, and it still is, pretty mysterious, and it's actually hard to study, right? Because imagine you have no tools, and someone was like, okay, do an experiment with light. It's like, all right, it's kind of difficult. It is. But for example, something that they did do actually when general relativity was hot on the block, right, just dropped. Everyone was like, all right, we need to see what's actually happening with general relativity. They had this whole event where a bunch of astronomers got together. I think it was this whole international thing, and they looked at an eclipse of the sun, a solar eclipse. And as predicted by general relativity, you could see stars that were actually behind the sun. How was that possible? Well, actually, the path that the light took actually went towards the back of the sun, right? And then curved around it into our eyes. And so it was actually one of the first confirmations that, Einstein's theories weren't just, they weren't just words on pages. It was actually like, okay, these stars are supposed to be hidden by the sun, but the light that came out of these stars was actually curved around. The path of the light was curved around the sun. And so, boom, there we go. Now we know that space-time curvature is actually a thing.
And another way to think about it is also think about Newton, right? Now, Newton says F equals GMM over R squared. Or, for those of you that might not be up to date with the latest equations, force is proportional to mass, right? The force of gravity is proportional to mass. Now, light happens to have no mass. So by Newton's laws of gravitation, light should not be touched by any massive object, right? Or so gravity should not be able to control light, basically, is what Newton would say. However, that's not true, because remember, gravity is not even a force, right? That's the whole idea behind the paper. And I think he puts it in a very succinct way, especially with the whole, because it's a very big thing to say. You know, Newton was, I mean, not that the force idea is wrong. It's just that Einstein's principles and his understanding of space and his representation of space agrees with Newtonian mechanics. It should.
It does.
It's not it's not like you can't use Newton. It's not like it's wrong. It's just that on a fundamental level, that's simply not what gravity is. You know, you can calculate the force. You can understand it as a force, because in that one episode, we spoke about how force and acceleration are related, right? And how acceleration is the key behind understanding the force. The only reason we say there's a force is because of the acceleration. So Einstein is like, yeah, there's no force. There's still acceleration. So that relationship is still there, and that's that Newtonian relationship. That relationship, force acceleration, it's still there, but we don't care about the force part. We just care about the acceleration, and I'm saying the acceleration depends on the mass of the body it's surrounding, right? So like, for example, on Earth, now you were even talking about time and how time bends along with this space thing, right? And a lot of people, might think, well, that's very interesting. Like, how does time also bend? Well, it's in a very similar fashion. Now, obviously, it's not a physical thing, but it bends in terms of slowing down or speeding up. So when you're near, like, a massive object like the Earth, for example, a spacecraft, let's say it's traveling completely straight line, there's nothing, absolute vacuum, you're just traveling in space, and then all of a sudden it encounters Earth. The time that the spacecraft experiences while encountering Earth technically is slowed down with respect to Earth. So Earth before, when it was in a vacuum, versus Earth when these guys are actually traveling through it, in that gravitational field, that's when their time slows down. So that's how time is also wrapped up in this whole shenanigan, right? And that's a very fundamental thing. I think that was even bigger of a thing that he proved, how time is related to space.
And what I love about this entire discussion is that maybe not every single one, but a lot of these ideas actually stem from the simple observation that the speed of light is constant. Because I actually read this on Wikipedia, not my words, but the speed of light is the conversion factor from space to time, or from time to space. And so if you have, if you have a constant and it's equal to, like, this is just an example, to get your brain thinking. But if you have a constant that is equal to, let's say, x times y, just two numbers being multiplied by each other, because you know that those are equal to a constant, then if x goes up, y has to go down. And if y goes up, x has to go down. Like, they're related in that way, you know what I mean? And so, for example, because we know that the speed of light is constant, it's almost like, the faster you go, the slower you experience time. And, also this is just some special relativity stuff, but it's kind of like, you always have to keep in mind that the thing that stays constant is light, and then the space and time is what bends in a way that whichever frame you're in, light will always stay that constant speed, right? And the beautiful thing about this is that it's all observer dependent, right?
You're right.
Because, like, living in a universe and being the fact that a universe exists and having observers within that universe is kind of synonymous, right?
Yeah.
If you have a universe with no observers in it, then does it really exist? Right? It's kind of up in the air, because
you're right.
There's nothing. It's that classic
philosophical question. You're right. You're right.
Exactly. It's pretty philosophical. Yeah. But, like, for example, like this. My idea is actually getting a little bit philosophical.
No, let's hear it. Let's hear it. Why
But
not?
No, I was gonna say, like, for example, if I look out into space and I see, like a certain effect of like special general relativity, would that effect still be a thing if nobody was there to see it? Like, this question doesn't really make sense. But
yeah, because
like,
I mean, it's that classic question, right? Like, if a tree falls in a forest, is like, did it really fall? Kind of question.
But would the laws of physics
and there's no observer kind of
even
thing,
exist, right? Because special relativity depends, and general relativity, it depends on the frame, right? And it depends on who's looking. But if there's nobody looking, then like, what do you?
Well, yeah, then it doesn't make any point. I mean, then there's no point though, because if no one's looking, you're not really. You don't really care about the system. So then, I mean, it's kind of like it's kind of like a, I mean, it's not a tautology, but it's kind of like a circular thing, because like that doesn't make any sense.
Contradiction.
Yeah, kind of like that kind of vibe, you know. So I mean, I'm not sure how true that is, but the biggest difference though, because
no, I don't know. I'm just
bouncing
I get ideas.
Yeah, no, but the biggest difference that you were talking about special relativity, and I mean, we have mentioned this previously before, but because we're talking about it, in this episode, we obviously have to. Special relativity versus general relativity, the biggest difference is that in special, you can literally think about it like a special case. It's a special case. The special case is when the frame of reference that you're in is inertial, meaning that, and we've spoken about this many, many, many times, that means the frame is like not accelerating, or it's traveling at constant velocity, or it's at rest, or something like that, right? So basically the frame is, so it's an inertial frame of reference. So that's your special case. Then we get general relativity, which is your general case. So that could be even accelerating frames of references. And that's actually where it pioneers, right?
Things get very complicated very quickly.
Oh, for sure. Because it's mainly because of the math, right? It's mainly the math required for general relativity is of a higher level, for sure, 100%. So it's just, it's a lot of combination of a lot of things. And I think we're going to touch on to some of it. Like the field equations, I know like we had that plan to just talk about it a little bit, so we're going to get into it. But it's really crazy, and it can definitely get exponentially harder, man. Because I believe it's a graduate level course, or of something of that level. Is it? No, but the actual general relativity, is it not? Is it an undergrad?
No, I have the option to take it in fourth year.
Interesting. But that's probably like an introduction. Anyway. You know what I mean?
I mean, whatever.
whatever. Anyways, not that matters. I just wanted to bring it up. It gets complicated.
Yeah.
Basically it.
If we look back at Newtonian mechanics, it says nothing about the speed of causality, because first of all, they didn't really know about it at that time. But also, it kind of begs the question, what if a very massive body were to appear somewhere in the universe? Would you feel its gravitational field like right away? Or, is there a speed at which that field actually travels until you feel it as well? And it's the same thing with electrodynamics, like charges. If a charge were to appear, when would you feel the electric field and all that stuff? Well, according to Newtonian mechanics, it would be, like, by assumption, I'm guessing, it would just be instantaneous, right? As soon as you have a body at a certain distance, as Ray said, the force is minus GMM over R squared. And so as soon as that body were to appear, you would feel the force, because that's you're in that situation where you can calculate the force immediately. But actually, gravitational fields travel at the speed of causality, the speed of light. And so, according to general relativity, the same situation, you would feel the effects of the gravitational, the space-time curvature, the gravitational force in quotation marks, if you want, at, the speed of light, or times the distance, or divided by the distance, or whatever.
Oh, no, but yeah,
divided by the speed of light.
It's going to travel at the speed of light, basically, is what you're trying to say.
Right.
So if it's a light minute away, it's going to take a minute to come.
Yeah. So you can think of this gravitational like tide, right? I don't want to say wave because we're going to use that word in a little bit, but this object is placed in space-time, and then the emanating gravitational tide that's going out in all directions is moving at the speed of light. And so you can kind of imagine this as placing like a bowling ball or dropping a bowling ball onto a trampoline. As soon as the bowling ball touches the tarp, then boom, you have this wave that goes all the way out to the edge of the trampoline. And if you're somewhere on that trampoline, you're going to feel that wave when it gets to you, not instantaneously. And so that's how you can like imagine it in your head. But what I was going to say is that, but the whole point of this discussion is that these gravitational fields travel at the speed of light. And so what happens I might give this off to Ray for a second, but what happens when two massive bodies are orbiting each other? Rayhan.
That's when it gets interesting, right?
Yeah.
So the idea behind these ripples that you were talking about, right, are basically, well, why? What causes them? That bowling ball and a trampoline. Well, it's not really how an object is formed in the universe, right? It doesn't just like pop into space time and just create a crazy ripple, right? So usually these ripples or these waves. Now we're gonna come to it. These waves are usually caused by ginormous events, like cataclysmic events. Usually like supernovae, black hole collisions, neutron star collisions, mergers, star mergers, galaxy mergers, obviously. So basically anything that will ripple this fabric that we call space-time, right? Like that classic trampoline example there. But now, what's interesting is, how do we know they exist? How do we know that these ripples can be experienced? Now, here's what's interesting about these ripples. Where is it actually taking place? It's literally taking place in the fabric of space-time. So what we call space, like this iPad in front of me, and obviously for the listeners you probably can't see that, but for this iPad in front of me, this space probably so this space is what is important, and this is what can be changed and malleable. It can actually be malleable, this space right over here, because of an influence of gravitational waves. So the idea behind these gravity waves is basically, okay, if something big happens, it's kind of like your simple example of something in a pond, right? And if you collide any two things, or any two things like in a whirlpool coming together or anything like that, that ripple effect that they will give out will basically be seen if it's a very clear pond, it'll be seen in the whole pond, right? Now, obviously, because of like earthly effects and stuff, it diminishes, but in reality, if it was a perfect system, the ripple would go on forever. So the idea of the gravity wave is very, very, very similar, and it propagates, as you were saying, at the speed of light. So whenever such a cataclysmic event occurs, it will reach us, however far that is, right, at the speed of light. And what's interesting again is, because this is traveling at the speed of light, and remember, what it's doing is that it's really moving space-time, there is a way for us to measure this movement. And that is when we get into
what I want you to do right now is close your eyes. Do you feel your body right now just moving and rippling with these gravitational waves? No, you don't, okay? That's
not really, no.
Moral of the story, no, you don't.
Not really.
Because these waves are actually stemming from an event very, very far away. For example, two black holes orbiting each other. And so due to the conservation of momentum, the closer they get, the faster they spin, the faster these waves are emanating away from this binary pair. And eventually they do actually collide, and they cause this gigantic outburst of gravitational wave all around. And so that's what, we have simulations predicting the shapes of these wave detections and all that stuff. And we're going to get into that in a second, because there are some actually very interesting things to talk about. What I was going to say is that, right, very far away, right? And so obviously, if you're very close, if you're right next to these two black holes, you will definitely feel these gravitational waves, okay?
For sure.
But obviously, the further away you are, the more precise you have to be, right? You need very, very precise, what's the word I'm looking for? Like technologically advanced tools in order to actually detect like very small ripples in space-time. And so before we actually talk about those tools, do you like gravity, Rehan?
I really do. I think I really do.
Listen, I love talking about gravity.
Yeah.
I love learning about gravity. And guess
I
what?
do too.
If you're a listener out there and you love talking about gravity and learning about gravity, head on over to brilliant.org. They actually have courses on gravitational energy, orbits in a gravity well, and get this, the fate of the universe, how gravity will affect the future.
That's
These
exactly
sound
what
like
I was looking for.
Amazing courses. Of course, all of Brilliant's courses are all, interactive. They teach you, they ask you questions, you learn. They also have daily challenges, which are always good for building that brain thinking, critical thinking ability. So yeah, head on over to brilliant.org.
You can also check us out. Link in the description below, and link also in the comment section, because I know some people appreciate that actually. Or you can just head over to brilliant.org/MPP. And the first 200 people that sign up, get this, get 20% off their first premium year.
My.
20% off. That's pretty crazy, right? That's pretty crazy. So head on over to brilliant.org/MPP, or link in the description, and go get yourself a premium subscription. Really worth it.
Definitely.
So getting back into how these detect, or what this technology is that can really detect these very small changes in space. Because even though we're talking about it like, oh, it's a cataclysmic event, the reality is it's probably moving like the width of one 1/100th of one, or 1/1000th of a proton. Like that's how much the space is really moving. So the space, so it's very, 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 very tiny. I'm talking like 10 to the minus like 17, 18 meters. Minus 18 meters. So that's a lot of zeros. So basically the point of the saying is, even though we are hyping these gravitational waves up as something that would be like, destroy all buildings, it really won't. And that could actually be taken as a problem. So how do we detect these things that, are vibrating at widths smaller than that of a proton? How do we do that?
And I think we actually talked a tiny bit about this with our quantum mechanics professor, who was on, I think it was episode number 43. Don't quote me on that. But we have what is called LIGO in the US. There's actually two LIGO observatories called, and LIGO stands for Laser Interferometer Gravitational Wave Observatory.
Exactly.
And
yes,
what does LIGO look like? Well, essentially, there's these two perpendicular arms that are actually 4 kilometers long. Imagine that. You want to go on a run? I wouldn't even be able to go back and forth. Maybe if I tried. But 4 kilometers, like you probably can't see the end of it, right? If you're standing on one end,
no, you
can't see the other end.
It's really far. Yeah, for sure.
Yeah. And so these arms essentially
perpendicular arms.
Yeah, perpendicular. They're essentially just chambers for shooting a laser through the chambers, and then they have mirrors where the laser bounces back and forth. And Rehan, why don't you tell us about how we actually detect these waves?
So for that, we got to start with interferometry, the basic understanding of interference of waves. So interferometry, as it's named, aptly named, is basically the study or experimentation with interference of waves. So something very interesting that we know about waves, and we know now light is also represented as waves. And something very interesting we know about these waves is that they interfere with one another. So we put two light waves together at the same amplitude at zero phase shift, or like together basically, they will double in amplitude. So it will amplify the light wave. But now let's say I send one of the light waves just a tad bit later. Or not later in time, but like it's technically a phase shift. It's like the distance at where it's sent. It's not a time, sorry. But if I do that, the amplitudes or the waves will be perfect enough to basically cancel each other out completely. Mm-hmm. And this is known as destructive and constructive interference, something I believe, as you said, we've spoken about various times before. Mm-hmm. And it's basically a fundamental property of all waves. All waves interfere, and they interfere constructively or destructively. And so now let's get into this idea. What is the idea of LIGO? Yeah.
So remember when we were talking about space-time curvature? Another way, like not another way, but maybe like a property of curvature is that it can stretch and compress things. Mm-hmm. That is because when you think of curvature, I know some people maybe think of like two-dimensional curvature where you're like literally like bending like something, like that. But in fact, compressing and stretching is a form of like three-dimensional curvature, 3D. Right?
Remember
so, as Ray just said, we're talking about light waves. Now, the frequency of light, the wavelength of light is very, very small. We're talking, hundreds of nanometers, okay? And we're talking about a distance, right? We have light traveling, back and forth, reflecting off of mirrors, tens of kilometers, right? Actually reflecting a lot more than...
we'll get into that.
Yeah, anyways.
We'll get into that.
The point is that imagine we send two beams of light, and on one way the light gets stretched and the other light gets compressed. It's a combination of both and everything at the same time. Mm-hmm. But as we're recording the intensity of the light, we see that at one moment they are constructively interfering, so we get like a spike in our detection, and then a little time, like a very, very, very small amount of time passes, and then suddenly it's destructive, and then constructive, and then destructive and constructive. So what's actually happening is that the distance, while the light is traveling through these chambers, the wavelength, right, is being compressed, stretched, compressed, and stretched.
Because of the compression of space,
exactly,
because of the gravity waves.
As the gravitational waves are passing through the observatory, it's stretching and compressing space. And we actually are able to see this by the detection of this interference of the light going up and down, up and down, up and down. And yeah. So,
how does it work? That's the big question, right? How does this thing work? So the idea stems from something known as a Michelson-Morley, or from the Michelson-Morley experiment, and it's known as a Michelson Interferometer, the idea that they use. So the Michelson-Morley experiment, just a quick history lesson here, pretty cool one, where Michelson and Morley, very clearly, wanted to prove that space was not empty. There was something called an ether that they had thought about that persists through all of space-time. And with this understanding of this ether, it needed to have traveled in a singular direction. So they devised this experiment, this interferometer, to basically test if this is true. So what they did was they set arms of equal length perpendicular to one another, where basically they would send light and force it to destructively interfere. Now, if it was destructive or constructive, I'm not entirely sure, but it's the same thing. It's just they wanted to measure a change in that intensity. So what they designed it to be, let's just say for now, was destructive interference. That means if, let's say, it moves in a certain way, theoretically what should happen is that we should see no light. That means they perfectly align. That means this width is exactly equal to this width. What I'm trying to show is the perpendicular widths are equal, and therefore no ether exists. Or if there was an interference, they would prove that the ether does exist because one of them is traveling faster than the other. That means there's something pushing it in one of the directions. Now, this experiment, obviously failed. The ether does not actually exist, but the idea of this experiment, the interferometer, and the way that they set it up was what was beautiful. So LIGO, very similar to this setup, just a little bit different, is basically very similar to this interferometer, where it has two perpendicular arms. However, 4 kilometers might seem a lot to us earthlings, but for gravity waves, where their change in space is on the order of 10 to the negative 17 meters, right? 4 kilometers is nothing. So what they did to amplify that, they added these things, a little technical here, called Fabry-Perot cavities. Fancy way of saying they added a mirror. That's basically what they did. So traditionally, what the setup is, I don't even think I really went through this, but there's a light, there's a laser, sorry. There's a beam splitter that basically splits the light in 2 perpendicular directions, right? That one light ray splits in 2, one going parallel and one going perpendicular, right? That's what a beam splitter does. Then the mirrors on the other side of the arms will basically reflect that light back into the beam splitter, and then it will direct it towards the photodetector, which will then see if there was an interference of light. Now, again, as I said, the 4 kilometers, not enough. So what they did was they added extra mirrors such that once it hit the beam splitter, it would go to the edge of the mirrors on the arms. It would reflect back and forth over 300 times and then come back to the beam splitter and re-meet at the photodetector. So the idea behind LIGO and what they set it up, and this I know for a fact, so that it was destructive interference. So at all times, there was nothing seen on the photodetector. Because remember, to see something, just a little bit, out of absolutely nothing is easier than to see something less out of something. Because if it was constructively interfering, right, and they had detected a gravity wave, it would just destruct by just a little bit, just a little bit. So it would be really hard to detect. But if it was destructive interference to begin with, and the gravity wave had come in, just a little bit would have actually produced something. So you would be able to see that a lot easier. So that was their idea behind this whole thing. And in 2015, as I mentioned, a little bit after they had revamped the whole facility, they have 2 facilities, by the way, one in Livingston and one in Hanford, and both of them must agree with each other because, again, sometimes it can just be an earthquake or it can be something specific to that area that's not really general. That's why they have these 2 facilities, and they're thinking about expanding, I believe, to India. I think that's another country that's going to get it. So something like that. It's going to be crazy. But anyways, the idea is basically to verify that the information is right. And what they did was, when this gravity wave occurred in 2015, basically the movement of space-time, remember, it's not like it happens like, it does, well, technically, but the thing is, it's all about catching it. It's all about timing it. Because this gravity wave actually occurred for fractions of a millisecond. In that millisecond, they had seen a spike, as in something was detected at the photodetector, and then it basically went back to what the regular noise levels were. So if you actually search for LIGO results, it's a very, very famous picture. You might be able to see it from any Google search. You'll be able to see what I'm kind of talking about, how it's kind of the spike and then it dies down a little bit. And it's a little more complicated because there are actually two sightings, but the idea again behind it was that moving, that space-time, as Parker, as you were saying, that movement of space-time is what caused one of those arms to shrink a little more than the other. And that's basically what caused some of that interference. And that's how it works. That's the workings of LIGO.
And so
super crazy.
The way we actually know that it's gravitational waves and not just anything else is that we have simulations, right? We have very, very fancy computers where we can, input the mass of black hole A, black hole B, and then, simulate what would happen, what we should detect if it was at this distance away from the Earth and we were like witnessing the event of them colliding together. And then we have like a specific shape for the wave, and then we can also test different events, like neutron stars rotating in like a binary pair and all that stuff. And it turns out that, we see the exact right results in these merger sightings with the LIGO observatory.
It was very, very close, yeah.
Yeah. One thing that, Rehan and I, we were taking an intro to astrophysics this year, and we had somebody come on in our class and talk about LIGO and gravitational waves and all that stuff. And one thing that I remember from that lecture was that, there was this this diagram with like black hole mass versus distance or something like that, anything, and also the color represented how it was detected. And essentially it was like, before we had LIGO, we had just like medium mass black holes, some massive ones, but it was really, it was not populated like that at all. Then what happened was that as soon as LIGO started popping off, we started seeing a lot of these black hole events. It turns out that the gravitational waves that they were analyzing were a little bit weird. And the reason is because they were only analyzing a certain interval for the possible masses, right? They're like, oh, we're probably not going to see black holes bigger than this. And so we're going to, cut it in between this interval and then see what we should be seeing. And what they were actually seeing is, the waves were a little bit off. They're like, okay, whatever. And then at some point, somebody said, hey, what if we try higher mass black holes? And all of a sudden, the waves started matching. They started checking out. And so I don't remember exactly what the figure is, but I think like the biggest black hole we had seen was like 80 times or like 50 times the mass of our sun. And then all of a sudden, we have like one that's 100, 120. And then as time goes on, we were actually finding more and more of these massive black holes through these gravitational waves. And so now, like, there's like an updated version of the diagram. You see a whole bunch of these black holes at the top part of the mass spectrum, all being detected via gravitational wave observation. So I thought that was pretty amazing.
They've detected I see here, 67 mergers. 67 mergers to date. So like neutron star, neutron black hole star. They've seen some pretty cool stuff. Because I would just imagine like a neutron black hole merger. Obviously they didn't really see that, but even detecting something like that, like comparing it to prediction, that must be like, damn, that must be like a really good feeling,
It's kind of like you stop and think about like where is this gonna lead us in the future? You know what I mean? Like, now we know that there's like big black holes, but like, what are we gonna do with that information?
Well, let's first back up a little bit and talk about, how did we even think of black holes to begin with? Ooh, what a question. I will be answering it, so don't worry. So how did we even think of the idea of black holes? And I think this is a kind of a nice one. So, not really think of the idea, but I'm going to say more mathematically speaking. This was more of a mathematical idea for the black hole, and I'll get to that. So in 1915, after the genius himself releases his paper on general relativity, along with Einstein's field equations, his famous, very, very famous field equations, he has his very famous, I'm not sure how many of you have maybe seen the field equation formula, but it's basically a bunch of, gibberish to anyone who's not like a doctorate or some level of some level of academic, right? So basically the gist of the field equation is that it relates two very important things. On one side of the field equations is what's represented by mass, energy, what's known as stress. So in, let's say, some area of space, what is the mass? What's the energy? So all of that is dictated by, again, I don't want to get too complicated because the math is a little complicated, but it's basically represented. Everything in the formula is represented by tensors, which are basically higher dimensional vectors, also known as matrices. So all of these things are basically in a matrix, and they're representing different properties of the space. So they're representing, as I was talking about, so one side of the equation, again, represents mass, energy, stuff like that, properties of the space. The other side of the equation represents curvature of the space. So what does that mean? That basically means what he's doing is he's relating the curvature of space-time to the mass and energy. So like the more mass, the more energy that a system has, for example, the sun versus the earth, the more curvature it will therefore have, which is what we see, right? And that relationship is what's very important, right? That's the relationship what's very important. Now, this guy releases it in 1915. 6 months later, before even Einstein himself really goes about solving these equations, Carl Schwarzschild comes out and he's like, yo, I got a solution. And he's like, what do you mean? He's like, I got a really crazy solution. I found a mathematical proof for an area of space with infinite curvature. Man, and people are like, what? What does that even mean? What does infinite curvature mean? How is that possible? Because remember, it relates curvature to mass and energy, right? Mm-hmm. So he's basically saying that there's an area of space with particular properties that will result in infinite curvature. And what he was, I think my video is, okay, that's fine. I think it just glitched out for a second. Oh, and what was I saying? And what he inevitably proved was the first mathematical idea of a singularity, a gravitational singularity, a singularity as in a point in space that has infinite curvature, that is infinitely curved. So it's kind of like a theoretical concept almost, right? And this was the first notion of a black hole, right? Every black hole has inherently a singularity. And that whole idea, again, if the idea itself, maybe it was, to be honest, maybe sprung before, but at least the mathematical idea of a singularity was first after the field equations. And I think that was a beautiful thing that he did there, because that truly got us thinking about, infinite curvature. How does that make sense? And then we start, generalizing these things called black holes. Imagine back in like 1920 saying that, hey, there's a point in space that'll suck you in. Like, you can't even perceive that, you know what I mean? Because it just made no sense. But now, look at where we are.
But it's so interesting, like black holes in general. Like, yeah. you think about a black hole. The size of a black hole is a zero, right? But the reason why we actually see an empty black dot is simply the physical properties of the black hole. That infinite curvature means that at some point, like, those funnels when you like donate money in those things and then the money like goes around, right? Like there's a point where like photons is like that money that you put in, and it could, like, if it's far enough away, right, the curvature is not that intense, it'll curve but keep going. There's also at the Schwarzschild radius, the photon sphere, where it'll curve and it'll just orbit. Like the photons will be satellites to the black hole and just orbit there, until something happens, I guess. But if you go past the photon sphere, then like the slope is too slippery for anything, right? As soon as you pass the photon sphere, there's oil, you can't get
leave.
Out. You're going on down on ice.
And interestingly enough, in a black hole, the more you struggle, the faster you go down. Just by the way that space is constructed. Even though inevitably you will die, the slowest way to die would be to stay completely still. Now, not that any of us are really going in a black hole anytime soon, but it was just an interesting thing that I had read somewhere, because the whole idea of a black hole is pretty cool. Because a fundamental thing that it does, and I think we've spoken about this before, and I know we're just kind of getting into black holes here a little bit, but I just wanted to talk about the whole idea of spaghettification, because I think it's really funny.
Wait, before you say that, I just want to say something that's really interesting is that as you're approaching a black hole, right? Like when you cross the Schwarzschild radius, you don't feel anything, right? Because it's empty space, right? So as you're approaching a black hole, what you see is like there's a black sphere in front of you, and then the universe is everywhere else where you see like stars and galaxies. As you cross the photon sphere, your field of vision actually becomes 50-50. In front of you, like if you look to the left and you look to the right, it'll be split. Even if you look up or down, in front of you will be completely black, and behind you will be universe. Mm-hmm. And when you enter the black hole and you turn around, it's like the opposite as when you were outside of the black hole. What happens is that your entire field of vision is black, and when you look behind you, there's this sphere that is the entire universe that is slowly shrinking and shrinking into nothingness as you approach the center of the black hole. So there's kind of this awesome I want to compare this to like particle and antiparticle, right? Like when you're outside of the black hole, there's universe, black hole, and when you're inside of the black hole, there's black hole, universe.
And the coolest thing about all this is that even though the light is so wonky, it's still traveling in straight lines with respect to itself, because it's just that space is so wonky in a black hole, and it's so curved that technically, by the definition of straight line, it is traveling in a straight line. It's just that the line itself has now been curved, which is really interesting. You know how you can make that classic line a circle? So it's basically that whole thing all over, and it's so cool because I think I was listening to this one. Wasn't it in a black hole where like you can see the back of your head or something?
When you're on the photon sphere,
you can see the back of your head, right? Yeah, that's pretty cool.
Because the photons are orbiting, so it goes like around and
so cool,
into
man.
your eyes.
But
one thing that's super interesting is time dilation. When you're in a strong gravitational field, your time slows down.
It does.
If let's say Rayhan, you go into a black hole.
Oh no.
According to me here on Earth, you would be immortalized. Because in my perspective, your time has dilated to infinity. And so you would just, I would be long gone before, and you would just still be chilling in the black hole.
So that's why the interesting thing about it is, but also another interesting thing about if you're looking at someone move into a black hole, you'll just see them there basically stagnant.
Yeah.
Until they die, until they basically just... Yeah. But because of how
once they actually cross the Schwarzschild radius, you wouldn't be able to see any update, right?
Yeah, any update, but you'll still see that same image because the light.
Before it
went in, right? And that's the whole cool concept behind this, the whole notion of, this whole thing is pretty fundamental, and it's nice. It's cool. Yeah. For sure.
So to those listening right now, I hope you enjoyed this discussion on gravitational waves, the force of gravity / space-time curvature, and black holes.
What was I just going to say? I was literally just going to say something before I botched that whole thing up.
Oh yeah, no, you're right. You were going to say something and I interrupted you.
No, I was talking about spaghettification. Screw that. No, that had nothing to do with it.
That's right,
but I wanted to talk about, time dilation. A cool thing about that. Did you know, if you stand near the pyramids, your time is moving slower than mine?
Wow.
Yeah. So the pyramids, right? I mean, I say the pyramids because it's a very massive object. But anything really very massive, if technically you're standing near it, believe it or not, obviously to fractions of seconds that you can't even perceive, but your time is actually traveling, or your time is being dilated. So it is being stretched. So you're basically traveling in a slower field because, not of a gravitational field or anything like that, no force, simply because of mass. Because of how mass curves space. And how when you're in that space, your time is now also dependent on that curved space. And that original discussion about how, just how time is bending, and bent time versus bent space, and understanding that relationship is pretty cool. Because we were thinking or at least I was thinking, how a higher dimensional being could cross a time barrier. Do you think that would be possible?
I don't know.
I don't know. I just had a random thought right now. I just had that super random thought while talking about bending time. I'm just like, I don't know. Well, it's a thought. It's a thought.
Maybe those 5-dimensional aliens will cross our little thin 4-dimensional little universe in their world.
Let's see, man.
Anyways,
I'm hoping for those aliens.
So yeah, if you enjoyed listening to this episode today,
make
sure to hit the follow button, subscribe button, the like button,
all the buttons.
Calling your name. It's literally calling your name. Just do it. Other than that, make sure to leave a comment. Any suggestions?
I keep saying this last because people already probably click out by the time this happens. Because like I should always say this first. Did you know that like 45? No. I think it's 55% of our watchers are not subscribed to us.
Damn.
I gotta mention this again in the beginning next time because we probably have no viewers actually watching this right now. But hopefully, if you are, just click subscribe. 55% of you aren't subscribed. Why not? Just a little bit.
This has been episode number 66 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. We'll see you soon.
Bye, guys.
See ya.